Hello, in this lecture we'll answer on two questions. In the first question, we'll find out the area of this trapezoid ABCD that blocks this circle. And in the second question, we'll find out the area of this green shape that is inside rectangle ABCD. So we'll start with the first question. In the drawing, we have trapezoid ABCD that blocks this circle. This circle is inscribed by trapezoid ABCD. In addition, we know that side AB of trapezoid ABCD equals to x units in its length. This is side DC is equals to 7 over x units in its length. This is angle BAD, that is a right angle. This is angle ADC, that is also a right angle. Again, our mission is to find out the area of this trapezoid ABCD that blocks this circle. So, first of all, what is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. Repeat again, a trapezoid is a quadrilateral with one pair of parallel sides. So here we have, this is trapezoid ABCD. Here side DC is parallel to the opposite side AB, and therefore this quadrilateral ABCD is defined as a trapezoid. Side DC, the two parallel sides are defined as the bases of the trapezoid. So side DC is the first base, side AB is the second base of trapezoid ABCD. If we define the length of the first base DC as A and the length of the second base AB as B, then the area of this trapezoid ABCD will be equal to the sum of its two bases, that is to say A plus B, times the height, that is h, over 2. Okay, again, the area of this trapezoid ABCD equals to the sum of its two bases, that is to say A plus B, times the height, that is h, over 2. The height h must create 90 degrees with the two bases. And indeed, the height h creates 90 degrees with the first base A, DC. This angle is right angle, and it creates 90 degrees with the second base AB, because this angle equals to 90 degrees and this angle equals to 90 degrees. So in conclusion, found out that the area of trapezoid ABCD equals to the sum of its two bases, that is to say A plus B, times the height, that is h, over 2. Okay? So first of all, we will define the points of tangencies of this trapezoid ABCD with the circle with letters. So we will define the point of tangency of tangent AB with this circle, this point, as E. Likewise, we define the point of tendency of tangent AD with this circle, this point, as F. And we define the point of tendency of tangent BC with this circle, this point, as G. And finally, we define the point of tendency of this tangent DC with this circle, this point, as H. So here we can implement rule 2. I'll repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. So in the drawing we have a circle. This is the common external point, point P. From this common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule, all two they are equal to each other. That is to say, PA equals to PB. So we can definitely implement rule 2 in our drawing. Why? Because in our drawing, we have, this is the common external point, point A. From this common external point, point A, we have two tangents to this circle, tangent AF and tangent AE. And according to rule 2, they are equal to each other. That is to say, AF equals to AE. So if we define the length of this tangent AE as Y, then the length of this tangent AF must be also equal to Y according to rule 2. Likewise, if we focus on this common external point, point B, from this common external point, point B, we have two tangents to this circle, tangent BG and tangent BE, and according to rule 2, they are equal to each other. That is to say, BG equals to BE. So if we define the length of this tangent BG as Z, then the length of this tangent BE must be also equal to Z according to rule 2. Likewise, if we focus on this common external point, point C, from this common external point, point C, we have two tangents to this circle, tangent CG and tangent CH. And according to rule 2, they are equal to each other. That is to say, CG equals to CH. So if we define the length of this tangent CG as M, then the length of this tangent CH must be also equal to M, according to rule 2. And finally, we'll focus on this common external point, point D. From this common external point, point D, we have two tangents to this circle, tangent DH and tangent DF. And according to rule 2, they are equal to each other. That is to say, DH equals to DF. So if we define the length of this tangent DH as T, then the length of this tangent DF must be also equal to T according to rule 2. In the next step, we will define the length of this side AD of trapezoid ABCD as A. Likewise, we will define the length of this side BC of trapezoid ABCD as B. So, what is the value of side AB plus side DC of trapezoid ABCD? AB plus DC. AB equals to Y plus Z plus DC. DC equals to T plus M. So, in total, AB plus DC equals to Y plus Z plus T plus M. Likewise, we let side AD to the opposite side BC. Trapezoid ABCD. So what is the value of AD plus BC? AD equals to y plus t plus BC. BC equals to z plus n. So in total we found out that AD plus BC equals to y plus t plus z plus m. Here we can change the orders of the letters in this expression according to the algebraic identity that a plus b equals to b plus a. We get that y plus t plus z plus m is equals to y plus z plus t plus m. So if we found out that AD plus BC equals to y plus z plus t plus m, and AB plus DC also equals to y plus z plus t plus m. So actually, those two expressions, AB plus DC and AD plus BC, they are both equal to the third same expression, that is y plus z plus t plus m, and therefore they are equal to each other. That is to say, AB plus DC is equals to AD plus BC. This is equation 1. I repeat again, according to equation 1, AB plus DC equals to AD plus BC. AB equals to x according to what is given as the equation, so we substitute AB by x plus DC. DC equals to 7 over x. DC equals to 7 over x, also according to what is given as the equation. So we substitute DC by 7 over x. And it is equals to AD. AD equals to A according to our definition, plus BC. BC equals to B also according to our definition. So in total we can find out that according to equation 1, x plus 7 over x equals to A plus B. And again, according to equation 1, we can find out that x plus 7 over x equals to A plus B. In the next step, we will do a construction. That is to say, from point B, we will draw perpendicular on DC. Again, from point B, we will draw perpendicular on side DC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point B and DC. This point is point S. Actually, by doing this construction, we can do quadrangle ABSD. This is quadrangle ABSD. Inside this quadrangle ABSD, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. Why? Because the sum of the other three angles is 270 degrees, so 270 degrees plus 90 degrees, it is equal to 360 degrees. That is the sum of the angles in any quadrangle. So inside quadrangle ABSD we have 4 right angles. And according to rule 6, any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to this quadrilateral ABSD as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. That is to say, rectangle ABSD, side AB must be equal to the opposite side DS. But AB equals to X according to what is given as equation, therefore DS must be also equal to S. Likewise, according to the same rule, in the same rectangle ABSD, side AD must be equal to the opposite side BS. But AD equals to A, therefore BS must be also equal to A. By doing this construction, we actually created the right triangle BSC. Repeat again, by doing the construction, we created the right ring triangle BSC. This is the right ring triangle BSC that we created. In this right ring triangle BSC, the hypotenuse BC equals to B, side BS equals to A. So what is the size, the length of this side SC? From the drawing it is very easy to see that SC equals to DC minus DS. Again, SC equals to DC minus DS. So I write it down. SC equals to DC minus DS. So SC equals to DC, that is 7 over X, according to what is given as the question, minus DS. We just right now found out that DS equals to X. So in total, SC equals to 7 over X minus X. So I write it down. This is side SC. That is equals to 7 over X minus X. So in the next step, I'll copy the right ring triangle BSC in a new page, and we will implement on this green right triangle BSC the Pythagoras theorem. Here by PT is a relation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Side SC equals to A units in its length. The hypotenuse BC equals to B units in its length. And finally, we just write down found out that side SC equals to 7 over X minus X units in its length. So actually, this is the right triangle. This again equals to 90 degrees, of course. So this is the right triangle, the right great triangle BSC that I copied from the original drawing. In this right triangle BSC, according to the Pythagoras theorem, BC square equals to BS square plus SC square. So I write it down. According to the Pythagoras theorem, in this right triangle BSC, BC squared, that is the square of the hypotenuse, equals to BS squared plus SC squared. BC squared, so BC is B, therefore BC squared is B squared, and it is equals to BS squared. BS is A, therefore BS squared is A squared plus SC squared. SC is 7 over x minus x, therefore SC squared is 7 over x minus x squared. So in conclusion, according to equation 2, we shall find out that b squared equals to a squared plus 7 over x minus x plus 7 over x minus x squared. So here we use the algebraic identity that states that a minus b squared equals to a plus b squared minus 4 times a times b. We use this algebraic identity for the value of this expression 7 over x minus x squared. So according to this algebraic identity, the value of 7 over x minus x squared, if we just substitute a by 7 over x and b by x, we'll get that 7 over x minus x squared, according to this algebraic identity, will be equal to 7 over x plus x squared minus 4 times a is 7 over x times b is x. In this expression we have x in the numerator and x in the denominator, so x will get cancelled. After cancelled x, we're left here with minus 4 times 7, that is minus 28. So in total 7 over x minus x squared, according to this algebraic identity, is equals to 7 over x plus x squared minus 28. Therefore, we can substitute 7 over x minus x squared in this equation 2 by 7 over x plus x squared minus 28. We will do it now, and we get that according to this equation 2, we have here b squared, that's equals to a squared, and here 7 over x minus x squared equals to 7 over x plus x squared minus 28. So according to equation 2, we can find out that b squared equals to a squared plus 7 over x plus x squared minus 28. So here we have 7 over x plus x squared, and according to equation 1, we actually found out that 7 over x plus x equals to a plus b. So I write it down. According to equation 1, we actually found out that 7 over x plus x equals to a plus b. here we will square this equation, equation 1, and we get that according to equation 1, 7 over x plus x squared equals to a plus b squared. Okay? And therefore, we can substitute 7 over x plus x squared in this equation, equation 2, by a plus b squared. We'll do it now, and we get that according to equation 2, we have here b squared, this is equals to a squared, plus 7 over x plus x squared. And we just write our formula that 7 over x plus x squared equals to a plus b. Therefore, we'll substitute 7 over x plus x squared in equation 2 by a plus b squared. And we have also here minus 28. So I copy this minus 28 in the equation 2. So in conclusion, we found out that according to equation 2, b squared equals to a squared plus a plus b squared minus 28. So here we'll open the brackets of this expression a plus b squared, and we get that according to this equation, equation 2, b squared equals to a squared plus a plus b squared. A plus b squared equals to a squared plus b squared plus 2 times a times b minus 28. So here we have b squared on both sides of the equation, so b squared will get cancelled. After we cancel b squared on this side of the equation, we left with nothing, that is to say 0. So 0 equals to, in the other side of the equation, we have a squared plus a squared, that is 2a squared, plus 2ab minus 28. So here we will add 28 to this equation, equation 2, and we get that according to this equation, equation 2, 0 plus 28 is 28. So 28 equals to 2a squared plus 2ab. So here we'll divide this equation, equation 2 by 2. And finally, we get that according to equation 2, (28 over 2 is 14), and it equals to 2a squared over 2 is a squared, plus 2ab over 2 is ab. So in conclusion, according to equation 2, we should find out that a squared plus ab equals to 14. This is according to equation 2, while according to equation 1, we have only found out that x plus 7 over x equals to a plus b. So we have here two equations. I'll repeat again. Our mission is to find out the area of this trapezoid, trapezoid ABCD. So what is the area of trapezoid ABCD? According to the formula that I presented to you in the beginning of the lecture, the area of trapezoid ABCD will be equal to the sum of its two bases. The two bases must be parallel to each other, times the height over 2. Again, the area of trapezoid ABCD equals to the sum of its two bases times the height over 2. And as I already mentioned before, the two bases must be parallel to each other. You can see in the drawing that in this trapezoid ABCD, side AD is definitely not parallel to side BC. So now we will prove that side AB is parallel to side DC. Why side AB is parallel to side DC? Because of the fact that we have here quadrilateral ABSD, that is a rectangle, and we know that the opposite sides of a rectangle are parallel to each other. So in rectangle ABSD, side AB is parallel to the opposite side DS. Again, in rectangle ABCD, side AB is parallel to the opposite side DS. But DS is part of the straight line DC. Again, DS is part of the straight line DC and is parallel to AB. And we know that if a part of a straight line is parallel to another straight line, then the straight line DC itself must be also parallel to the other straight line, that is AB. So in conclusion, we should find out that side DC is parallel to the opposite side AB, and therefore the two bases in trapezoid ABCD are AB and DC. And therefore the sum of the two bases is actually AB plus DC. So the area of trapezoid ABCD equals to the sum of the two bases of trapezoid ABCD, that is to say AB plus DC times the height over 2. The height must create 90 degrees with the two bases. And here you can see that side AD creates 90 degrees with the base AB, and it creates also 90 degrees with the base DC. This again equals to 90 degrees. Therefore the height is AD. The height is AD over 2. So the height of trapezoid ABCD equals to AB plus DC times AD over 2. AB equals to X according to what is given in the question, plus DC equals to 7 over X according to what is given in the question also. So in conclusion, I should find out that the area of trapezoid ABCD equals to X plus 7 over X times AD over 2. But according to equation 1, X plus 7 over X equals to A plus B. So we substitute X plus 7 over X in this expression by A plus B. And we get that X plus 7 over X is A plus B. So in total, this expression equals to A plus B times AD over 2. But according to our definition, side AD equals to A. So we substitute AD by A. We substitute AD by A. In total, we actually found out that the area of trapezoid ABCD equals to A plus B times AD, that is A over 2. So here we'll open the brackets of this expression and we get that A times A is A squared plus AB over 2. But according to equation 2, A squared plus AB equals to 14. Repeat again. According to equation 2, A squared plus AB equals to 14. Here, according to equation 2, A squared plus AB equals to 14. Therefore, we substitute A squared plus AB in this expression by 14. So in total, this expression equals to 14 over 2, that is 7. In conclusion, we found out that the area of trapezoid ABCD equals to 7 square units. I repeat again, the area of this trapezoid ABCD equals to 7 square units. So we finished with the first question. In the next step, I present to you the second question, and we solve the second question. Our mission in the second question is to find out the area of this green shape. So in the drawing we have rectangle ABCD. We know that this is side CB of rectangle ABCD, that is equals to 7 units in its length. Here CB equals to 7. In addition, we know that this is line segment CP, that is equals to 4 units in its length. This is line segment PQ, that equals to 2 units. And finally, this is line segment QA, that is equals to 5 units in its length. In addition, this is angle CPQ, that is a right angle, and this is angle PQA, that is also a right angle. I repeat again that our mission is to find out the area of this green shape. So in the first step, we'll join point C and A together by a straight line. And we'll define the intersection point of diagonal CA of rectangle ABCD with line segment PQ, this point, as point M. We'll define the length of this line segment PM as X. So what is the length of line segment MQ? From the drawing it is very easy to see that MQ equals to PQ minus PM. Again, MQ equals to PQ minus PM. So I'll write it down. MQ equals to PQ minus PM. So MQ equals to PQ, that is 2 according to what is given as the question, minus PM. PM is X according to our definition. So in total, MQ equals to 2 minus X. So MQ equals to 2 minus X, units in its length. By joining points A and C together by a straight line, we can deduce 2 vertex angles. Angle CMP is defined as the first vertex angle, and this is angle AMQ, that is the second vertex angle. And we also know that vertex angles are equal to each other. So if we define this vertex angles PMC as theta, then the other vertex angles AMQ must be also equal to theta. The next step will focus on this white right triangle AMQ. In this white right triangle AMQ, this angle equals to theta, this angle equals to 90 degrees, therefore the third missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is equals to 180 degrees, that is the sum of the angles in any triangle. Likewise, if we focus on this small green triangle PCM, this angle equals to theta, this angle equals to 90 degrees, therefore the missing third angle must be equal to 90 degrees minus theta. So write it here also, angle PCM must be equal to 90 degrees minus theta. Okay, in the next step, we prove that those two right triangles are similar to each other. That is to say, we prove that the right y triangle AMQ is similar to this right small green triangle PMC. So write it down. We prove that the right y triangle AMQ is similar to this right green small triangle PMC. So why those two right triangles are similar to each other? First of all, those two angles, they are both equal to theta, therefore they are equal to each other. So actually, this is angle AMQ in the right triangle, the right triangle AMQ, and it is equals to this angle, it is actually angle PMC in the right triangle PMC. So I repeat again. Angle AMQ in the right triangle AMQ, the right triangle AMQ equals to angle PMC in the right green small triangle PMC. They are both equal to theta, therefore they are equal to each other. In addition, those two angles, they are both equal to 90 degrees, they are right angles, therefore they are equal to each other. So actually, this is angle MQA. In the right triangle MQ, and it is equal to this angle, that is actually angle CPM in the right green small triangle PMC. So repeat again, angle MQA in the right triangle AMQ, the right triangle AMQ equals to angle CPM in the right green small triangle PMC. They are both equal to 90 degrees, therefore they are equal to each other. And finally, those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So this is angle MAQ. The right triangle AMQ, and this equals to this angle, that's actually angle PCM in the right green small triangle PMC. So repeat again, angle MAQ in the right triangle AMQ equals to angle PCM in the right green small triangle PMC. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So we actually proved that all the triangles in this right triangle AMQ are correspondingly equal to all the triangles in this right green small triangle PCM, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. Actually proved that the right right triangle AMQ is similar. This is the sign of similar to the right green small triangle PMC according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we conclude that the following relationship exists between their sides. We conclude that side PM in the right green small triangle PMC over side MQ in the right triangle AMQ is equals to side PC in the right green small triangle PMC over side AQ in the right triangle AMQ. Okay, again, we conclude that PC over MQ equals to PM over MQ equals to PC over AQ. PM equals to X according to our definition. So we substitute PM by X over MQ. MQ equals to 2 minus X. And it is equals to PC, that is 4, according to what is given as a question, over AQ, that is 5, also according to what is given as a question. So in conclusion, I actually found out that x over 2 minus x equals to 4/5. Here we cross multiply this equation, and we get that five x equals to 4 times 2 minus x. So here we'll open the brackets on this side of the equation, and we get that 5x equals to 4 times 2 is 8 minus 4x. Here we'll add 4x to this equation, and we get that 5x plus 4x is 9x, so 9x equals to 8. Here we divide this equation by 9, and finally we get that x equals to 8 over 9, or x equals to 8 ninths. So we found out that the length of the line segment PM is equal to x is equals to 8 ninths. So what is the length of line segment MQ, that is 2 minus x? 2 is 18 ninths. Again, 2 is 18 ninths, and therefore 2 minus x is 18 ninths minus x. So it is 18 ninths minus x is 8 ninths. So in total, 2 minus x equals to 18 ninths minus 8 ninths. 18 ninths minus 8 ninths equals to 10 ninths. So in conclusion, we found out that the length of this line segment MQ that equals to 2 minus x equals to 10 ninths, while the length of this line segment PM that's equal to x is equals to 8 ninths. So in the next step, I'll copy this line AQPC in a new pattern. We'll analyze this line segment. We'll analyze this line AQPC. Side AQ equals to 5 units in its length, according to what is given as the question. Side QP equals to 2 units. AQP, this angle is a right angle. Side PC equals to 4 units in its length, according to what is given in the question. And this is angle MPC, it is a right angle. So actually, this is line AQPC that I copied from the original drawing. We will extend the straight line AQ by straight line. I repeat again, we will extend the straight line AQ by straight line. Actually, when you extend a straight line by straight line, the result is a straight line. So this is a straight line. So if you focus on the upper side of this straight line at point Q, here the sum of the angles must be equal to 180 degrees. According to rule 3, that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of this straight line at point Q? We have this angle that is a right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we will do a construction. That is to say, from point C, we will draw perpendicular on the extended AQ. Again, from point C, we will draw perpendicular on the extended AQ. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C, the extended AQ, as point N. By doing this construction, we added the quadrilateral PC and Q. Inside this quadrilateral PC and Q, we have 1, 2, 3 right angles. And the sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the fourth missing angle must be equal to 90 degrees in its size. So inside this quadrilateral PC and Q, we have 4 right angles, and according to rule 6, any quadrilateral that has 4 right angles must be this rectangle, if not a square. So we relate to this quadrilateral PC and Q as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle PC and Q, side PC must be equal to the opposite side CN. But PQ is 2, therefore CN must be also equal to 2. Likewise, according to the sum rule, in the same rectangle PC and Q, side PC must be equal to the opposite side QN. But PC is 4, therefore QN must be also equal to 4. In the next step, we will join points A and C together by a straight line. Actually, by joining points A and C, create the right triangle ACN. So in the next step, we will implement the Pythagoras theorem on this right triangle ACN. Here by PT is abbreviation for Pythagoras theorem. So according to the Pythagoras theorem, in this right triangle ACN, AC squared, that is the square of the hypotenuse, must be equal to CN squared plus AN squared. Repeat again, according to the Pythagoras theorem, in the right triangle ACN, AC squared equals to CN squared plus AN squared. So AC squared equals to Cn squared. Cn is 2, therefore Cn squared is 2 squared, that is 4, plus an square. An in total equals to 5 plus 4, that is 9. Again, an in total equals to 5 plus 4, that is 9. Therefore, an square is 9 squared, that is 81. So in total, actually found out that AC square equals to 4 plus 81, that is 85. So AC square equals to 85. It is given us the question that ABCD is a rectangle, and you know that all the angles inside any rectangle are right angles. So this is angle ABC, that is a right angle. In the next step, I will copy the right big triangle ABC in the new page, and we will implement on this right big triangle ABC the Pythagoras theorem. Here by PT is the abbreviation for Pythagoras theorem. We just right now found out that AC squared equals to 25. That is the square of the hypotenuse of the right triangle ABC. And according to what is given as the question, side CB equals to 7 units in its length. So actually, this is the right triangle ABC that I call it from the original domain. In this right triangle ABC, AC square equals to AB square plus CB square. AC square is 85, and it is equals to AB square. AB is the missing side, so we leave it as it is. So it is AB square plus CB square. CB is 7, therefore CB square is 7 squared, that is 49. So in conclusion, we found out that 85 equals to AB square plus 49. Here we subtract 49 from this equation, and we get that AB square equals to 85 minus 49 is 36. So AB square equals to 36. Here we take a root out of this equation. And finally we get that AB equals to the square root of 36, that is 6. So AB equals to 6 units in its length. So actually, this is side AB, and it is equals to 6 units in its length. Our mission is to find out the area of this green shape. So what is the area of the green shape? Actually, the area of the green shape equals to the area of the right big triangle ABC. And because of the fact that the area of the big right triangle consists of also the area of this white right triangle AMQ, and we interest us only on the green area, we have to subtract from the area of the right triangle ABC the area of this right triangle AQM. So the area of the green shape equals to the area of the big right triangle ABC minus the area of the right triangle AQM, and because of the fact that the area of the right big triangle ABC is not include this triangle, green right triangle PCM, we have to add to the area of the big right triangle ABC the area of this green small right triangle PCM. So it is plus the area of the green small right triangle PCM. So in conclusion, we found out that the area of the green shape equals to the area of the big right triangle ABC minus the area of the right triangle AQM plus the area of the right green triangle PCM. Repeat again, the area of triangle ABC, the area of the green shape equals to the area of the big right triangle ABC minus the area of the right triangle AQM plus the area of this green small right triangle PMC. So the area of the green shape equals to the area of the big right triangle ABC. The area of the big right triangle ABC equals to the base of the triangle that is AB times the height to the base that is CB over 2. Repeat again. The area of the big right triangle ABC in total it is equals to the base that is AB times the height of the base that is CB over 2 minus the area of the white right triangle AQM. The area of this white right triangle AQM equals to the base that is AM, the base that is AQ, the base is AQ, times the height to the base that is QM over 2. Repeat again, the area of this the area of this white right triangle AMQ equals to the base that is AQ times the height that is QM over 2 plus the area of the right green small triangle PCM. The area of this green right triangle PCM equals to the base that is PC times the height to the base that is PM over 2. Repeat again. Found out that the area of the green small right triangle PCM equals to the base that is PC times the height that is PM over 2. So the area of the green shape equals to the area of triangle ABC that is AB times CB over 2. AB is 6 times the base CB is 7 over 2. So in total the area of the big right triangle ABC equals to 6 times 7 over 2 minus the area of the right triangle AQM that is equals to AQ that is 5 times QM that is 10/9 over 2. So actually in conclusion, we found out that the area of the right triangle AQM equals to 5 times 10 over 2 times 9 plus the area of the green small triangle PCM that is PC is 4 times PM that is 8/9 over 2. So we found out that the green small right triangle PCM equals to 4 times 8 over 2 times 9. So here the area of the big right triangle ABC equals to 6 times 7 over 2. 6 times 7 is 42 and 42 over 2 is 21. So the area of the big right triangle ABC equals to 21 square units. The area of the white triangle AQM equals to this expression. So here we have 10 over 2 is 5 and 5 times 5 is 25. So in total this expression equals to minus 25 over 9 plus the area of the green small triangle PCM is equal to this expression. So this expression equals to 8 over 2 that is 4 and 4 times 4 is 16. So in total this expression equals to 16 over 9. So if we focus on these two expressions, 9 is the common factor in the denominator. Therefore, here the area of the green shape equals to 21, and here we have minus 25 plus 16 is minus 9, and 9 is the common factor, so in the denominator we have 9. So in total the area of the green shape equals to 21 minus 9 over 9. So it is 21 and minus 9 over 9 is minus 1. So the area of the green shape equals to 21 minus 1, that is 20. In conclusion, we found out that the area of the green shape equals to 20 square units. Repeat again. The area of this green shape equals to 20 square units. So in the next step, I will summarize the lecture. We start with the first question. In the first question, our mission is to find out the area of this trapezoid ABCD. So, in the drawing, we have a circle that is inscribed by this trapezoid ABCD. In addition, we know that side AB of the trapezoid equals to x units in its length, side DC equals to 7 units, 7 over x units in its length. This angle is right angle, and this is also a right angle. Again, our mission is to find out the area of this trapezoid ABCD. So, what is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. So again, a trapezoid is a quadrilateral with one pair of parallel sides. Here we have trapezoid ABCD. The two parallel sides are DC and AB. That is to say, DC is parallel to AB. And therefore, the two bases are the two parallel sides. That is to say, DC is the first base and AB is the second base. And the area of this trapezoid ABCD equals to the sum of its two bases. If we define the length of base DC as A and the length of base AB as B, the sum of the two bases will be equal to A plus B times the height, that is h over 2. Repeat again, the area of trapezoid ABCD equals to A plus B times h over 2. The height h must create 90 degrees with the two bases. Here, this angle is 90 degrees and this angle is also 90 degrees. So in conclusion, we found that the area of trapezoid ABCD equals to the sum of its two bases, that is A plus B, times the height, that is h over 2. So in the first step, we defined the point of tendencies of this trapezoid ABCD with this circle with letters. We defined the point of tendency of tangent AB with this circle, this point as C. We defined the point of tendency of tangent AD with this circle, this point as F. We defined the point of tendency of tangent BC with this circle, this point as G. And finally, we defined the point of tendency of tangent DC with this circle, this point as H. So here we can implement rule 2. According to rule 2, the lengths of two tangents from a common extreme point to a circle are equal. So in the drawing we have a circle, and we have, this is the common extreme point P. From this common extreme point P, we have two tangents to the circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can definitely implement rule 2 in our drawing. Why? Because in our drawing, if you focus on this common extreme point A, from this common extreme point A, we have two tangents to the circle, tangent AE and tangent AF. And according to rule 2, they are equal to each other. That is to say, AE equals to AF. So if we define the length of tangent AE as y, then the length of this tangent AF must be also equal to y according to rule 2. Likewise, we focus on this common extreme point P. From this common extreme point B, we have two tangents to this circle, tangent BE and tangent BG. And according to rule 2, they are equal to each other. That is to say, BE equals to BG. So if we define the length of this tangent BE as Z, then the length of this tangent BZ, the length of this tangent BG must be also equal to Z according to rule 2. We focus on this common extreme point C. From this common extreme point C, we have two tangents to the circle, tangent CG and tangent CH. And according to rule 2, they are equal to each other. That is to say, CG equals to CH. So if we define the length of this tangent CG as M, then the length of this tangent CH must be also equal to M. And finally, we focus on this common extreme point D. From this common extreme point D, we have two tangents to the circle, tangent DH and tangent DF. And according to rule 2, they are equal to each other. That is to say, DH equals to DF. So if we define the length of this tangent DF as T, then the length of this tangent DH must be also equal to T according to rule 2. In the next step, we actually defined the length of side AD as A, and the length of this side BC of trapezoid ABCD is B. So what is the value of AB plus DC? AB equals to Y plus Z, DC equals to T plus M. So in total, AB plus DC equals to Y plus Z plus T plus M. Likewise, we added side AD to the opposite side BC. What is the value of AD plus BC? AD equals to Y plus T and BC equals to Z plus M. So in total, AD plus BC equals to Y plus T plus Z plus M. Here we can change the orders of the letters or the variables of this expression. According to the algebraic identity that A plus B equals to B plus A, we get that Y plus T plus Z plus M will be equal to Y plus Z plus T plus M. So AB plus DC equals to Y plus Z plus T plus M, and AB plus DC also equals to Y plus Z plus T plus M. So those two expressions in the green color, they are both equal to the same third expression, that is to say Y plus Z plus T plus M, Y plus Z plus T plus M, and therefore they are equal to each other. That is to say, this expression AB plus DC equals to this expression that is AD plus BC. So in conclusion, we found out that according to equation 1, AB plus DC equals to AD plus BC. AB is X, DC is 7 over X, AD is A, and BC is B. So in total, actually, according to equation 1, we actually found out that X plus 7 over X equals to A plus B. In the next step, we did the construction, that is to say, from point B, we do perpendicular on DC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B, and we define the touching point of the perpendicular from point B and DC. This point is point S. By doing this construction, created quadrangle ABSD. So inside quadrangle ABSD, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore this fourth missing angle must be equal to 90 degrees inside. So inside quadrangle ABSD we have 4 right angles, and according to rule 6, any quadrangle that has 4 right angles must be at least a rectangle, if not a square. So we relate to this quadrangle ABSD as a rectangle. But we also know that the opposite sides of rectangle are equal to each other. So in rectangle ABSD, side AB must be equal to the opposite side SD. But AB is X, therefore SD must be also equal to X. Likewise, according to the same rule, in the same rectangle ABSD, side AD must be equal to the opposite side BS. But AD is A, therefore BS must be also equal to A. By doing this construction, we created the green right angle BSC. In the green right angle BSC, BS equals to A, the hypotenuse BC equals to B. So what is the length of SC? Side SC of the green triangle? Side SC equals to DC minus DS. Again, SC equals to DC minus DS. DC is 7 over X, DS is X. So in total, SC equals to 7 over X minus X. In the next step, I copied this right green triangle in a new page and implemented the Pythagoras theorem with this green right triangle BSC. This is the green right triangle BSC that I copied from the original domain. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. In the right triangle BSC, it means that BC square equals to BS square plus SC square. Again, BC square equals to BS square plus SC square. So BC is B, therefore BC square is B square, and it is equals to BS square. BS is A, therefore BS square is A square plus SC square. SC is 7 over X minus X, therefore SC square is 7 over X minus X square. So according to equation 2, we actually found out that B square equals to A square plus 7 over X minus X square. Here we have the algebraic identity that A minus B square equals to A plus B square minus 4 times AB. According to this algebraic identity, the value of the expression 7 over X minus X square, if we just substitute 7 over X by A and X by B, we get that 7 over X minus X square will be equal to 7 over X plus X square minus 4 times A is 7 over X times B, that is X. So here we have X in the denominator and X in the denominator, so X will get cancelled. So in total this expression after we cancelled X will be equal to minus 4 times 7, that is minus 28. So in conclusion, actually found out that 7 over x minus x squared according to this algebraic identity equals to 7 over x plus x squared minus 28. Therefore, we can substitute 7 over x minus x squared in this equation 2 by 7 over x plus x squared minus 28. We did it and found out that according to this equation 2, b squared equals to a squared, and 7 over x minus x squared equals to 7 over x plus x squared minus 28, according to this algebraic identity. So according to equation 2, we actually found out that b squared equals to a squared plus 7 over x plus x squared minus 28. So here, according to equation 1, 7 over x plus x equals to a plus b. Repeat again, according to equation 1, we already found out that 7 over x plus x equals to a plus b. Here we will square this equation 1, and we get that 7 over x plus x squared equals to a plus b squared. Therefore, we can substitute 7 over x plus x squared in this equation 2 by a plus b squared. We did it, and we got that b squared equals to a squared, and again 7 over x plus x squared equals to a plus b squared. So here, according to equation 2, actually found out that b squared equals to a squared plus a plus b squared minus 28. Here actually, in equation 2, we have 7 over x plus x squared, and 7 over x plus x squared equals to a plus b squared, and therefore b squared equals to a squared, and 7 over x plus x squared equals to a plus b squared, and we have also minus 28 in this equation 2, so I copy minus 28 here. So in conclusion, according to equation 2, we found out that b squared equals to a squared plus a plus b squared minus 28. Here we open the brackets of this expression, and found out that b squared equals to a squared, and a plus b squared equals to a squared plus b squared plus 2 times ab minus 28. Here we have b squared on both sides of the equation, so b squared will get cancelled. After cancelled b squared on this side of the equation, we left with nothing, that is to say 0. Here a squared plus a squared is 2a squared plus 2ab minus 28. Here we added 28 to this equation 2, and finally found out that 0 plus 28 is 28, so 28 equals to 2a squared plus 2ab. Here we divided this equation 2 by 2, and finally found out that 28 over 2 is 14, so 14 equals to 2a squared over 2 is a squared, plus 2ab over 2 is ab. So in total, according to equation 2, we actually found out that 14 equals to a squared plus ab. This is according to equation 2, while according to equation 1, we have already found out that x plus 7 over x equals to a plus b. Now our mission is to find out the area of this trapezoid ABCD. So what is the area of trapezoid ABCD? The area of trapezoid ABCD, according to the formula that I presented to you in the beginning of the lecture, will be equal to the sum of its two bases times the height over 2. The two bases must be parallel to each other. Here you can definitely see that side AD is not parallel to side BC. Now we prove that side AB is parallel to side DC. Why side AB is parallel to side DC? Because of the fact that ABSD is a rectangle. We know that the opposite sides of a rectangle are parallel to each other. So in rectangle ABSD, side AB is parallel to side DS. But DS is part of the side line DC and is parallel to AB. So if part of the side line is parallel to another side line, then the side line DC itself must be also parallel to the other side line, that is AB. So in conclusion, we found that DC is parallel to AB, and therefore the two parallel sides are DC and AB, and therefore there are two bases of this trapezoid ABCD. So the sum of the two bases is AB plus DC. So the area of trapezoid ABCD equals to the sum of the two bases, that is AB plus DC, times the height over 2. The height must create 90 degrees with the two bases. And you can see here that AD, side AD creates 90 degrees with the base AB, this angle equals to 90 degrees, and it also creates 90 degrees with the base DC. This angle also equals to 90 degrees. So the height is AD. So the height is AD, so in total, the area of trapezoid ABCD equals to the sum of its two bases, that is AB plus DC, times the height, that is AD over 2. AB is x, DC is 7 over x, times AD over 2. So the area of trapezoid ABCD equals to x plus 7 over x times AD over 2. But x plus 7 over x, according to equation 1, equals to a plus b. So we substitute x plus 7 over x by a plus b, and found out that here x plus 7 over x is a plus b times AD over 2. AD is a, so we substitute AD by a. So in total, we actually found out that the area of trapezoid ABCD equals to a plus b times a over 2. Here we open the brackets of this expression and found out that a times a is a squared plus ab over 2. But a squared plus ab according to equation 2 is equals to 14. So we substitute a squared plus ab by 14. So this expression in total equals to 14 over 2, that is 7. In conclusion, we found out that the area of this trapezoid ABCD equals to 7 square units. We finished with the first question. In the next step, I will present to you the second question. We solved the second question. Okay, again, our mission in the second question is to find out the area of this grand shape. So in the domain we have rectangle ABCD, side CB equals to 7 units in its length, line segment CP equals to 4 units in its length, side segment PQ equals to 2 units in its length, line segment QA equals to 5 units in its length. This angle is a right angle, and this angle PQA is also a right angle. Again, our mission is to find out the area of this grand shape. So first of all, we join points A and C together by a straight line. And we define the intersection point of diagonal CA with line segment PQ, this point SM. We define line segment PM as X. So what is the length of line segment MQ? MQ equals to PQ minus PM. Again, MQ equals to PQ minus PM. So MQ equals to PQ, that is 2, minus PM, that is X. So in total, MQ equals to 2 minus X. By doing this construction, we actually created here two vertex angles, and we know that vertex angles are equal to each other. So if this angle is theta, then another angle must be also equal to theta. And then we focus on this white right triangle AQM. This white right triangle AQM, this angle equals to theta, this angle equals to 90 degrees. Therefore, the missing angle here must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees this equals to 180 degrees, that is the sum of the angles in the triangle. Likewise, according to the same logic, in the right triangle CPM, this angle equals to theta, this angle equals to 90 degrees, therefore the fourth missing angle must be equal to 90 degrees minus theta. In the next step, we proved that those two right triangles are similar to each other. That is to say, the right triangle AQM is similar to the right small triangle PCM. So why those two right triangles are similar to each other? First of all, those two angles are both equal to theta, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So I actually proved that all the three angles in the right triangle AMQ are corresponding equal to all the three angles in the right small triangle PCM, therefore those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that following relationship exists between their sides. That side PM in the right triangle PCM over side MQ in the right triangle AQM equals to side PC, the right triangle, over side AQ in the right triangle. Repeat again, we derive that PM over MQ equals to PC over AQ. PM is X, MQ is 2 minus X, PC is 4 and AQ is 5. So in conclusion, we found out that X over 2 minus X equals to 4 fifths. Here, of course, multiply this equation and finally found out that 5x equals to 4 times 2 minus x. Here we open the brackets of this expression and finally found out that 5x equals to 4 times 2 is 8 minus 4x. So 5x equals to 8 minus 4x. Here we added 4x to this equation and finally found out that 8 equals to 4x plus 5x is 9x. So 9x equals to 8. Here we divided the equation by 9 and finally found out that x equals to 8 9ths. So here x 97 p.m. that equals to x is equals to 8 9ths. So what is the value of 97 mq? 97 mq equals to 2 minus x. 2 is 18 9ths. Therefore 2 minus x is 18 9ths minus x. And x is 8 9ths, so in total 2 minus x equals to 18 9ths minus 8 9ths, that is 10 9ths. So qm equals to 10 9ths and pm equals to 8 9ths. In the next step, I copy this line AQPC in a new page and analyze this line AQPC. This is the line AQPC that I copied from the original domain. AQ is the straight line. We extended the straight line AQ by straight line. When you extend the straight line by straight line, the result is a straight line. So this is a straight line. If we focus on the upper side of this straight line at point Q, we have the sum of the angles must be equal to 180 degrees. According to rule 3. So which angles we have the upper side of this straight line at point Q? We have this angle that is a right angle plus this missing angle. In total, the sum of those angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we did the construction, that is to say from point C, we do perpendicular on the extended AQ. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C, this extended AQ as N. By doing this construction, we created here quadrilateral PC and Q. Inside quadrilateral PC and Q, we have 1, 2, 3 right angles, and therefore the fourth angle must be also equal to 90 degrees according to the rule that the sum of the angles in any quadrilateral is equals to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its side. So inside quadrilateral PC and Q, we have 4 right angles, and according to rule 6, any quadrilateral that has 4 right angles must be at least a rectangle plus a square. So we relate to this quadrilateral PC and Q as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle PC and Q, side QN must be equal to side PC. But PC is 4, therefore QN must be also equal to 4. Likewise, according to the sum rule, in this rectangle PC and Q, side CN must be also equal to side PQ. But PQ is 2, therefore CN must be also equal to 2. In the next step, we join points A and C together by straight line. By joining points A and C, we created the right triangle CN. So in the next step, we implemented the Pythagoras theorem in the right triangle CN. According to the Pythagoras theorem, the right triangle CN, AC square equals to CN square plus AN square. So AC square equals to CN square. CN is 2, therefore CN square is 2 square, that is 4. Plus AN square. AN in total is 5 plus 4, that is 9. Therefore, AN square is 9 square, that is 81. So in conclusion, I actually found out that AC square equals to 4 plus 81, that is 85. So AC square equals to 85. It is given as the question that ABCD is rectangle. We know that all the angles inside any rectangle are right angle. All the angles inside any rectangle are right angles. So this angle ABC is a right angle. So in the next step, I copied the right triangle ABC in a new page and implemented the Pythagoras theorem. This right triangle ABC. This is the right triangle ABC that I copied from the original drawing. This right triangle ABC, according to the Pythagoras theorem, AC square equals to AB square plus CB square. So AC square is 85, and it equals to AB square. AB is the missing side, so leave it as it is, plus CB square. CB is 7, therefore CB square is 7 square, that is 49. So in conclusion, we actually found out that 85 equals to AB square plus 49. Here we subtract 49 from this equation, and finally found out that AB square equals to 85 minus 49, that is 36. So AB square equals to 36. Here we took a root out of this equation, and finally found out that AB equals to the square root of 36, that is 6. This is side AB, is equals to 6 units in itself. Our mission is to find out the area of the green shape. The area of the green shape equals to the area of the big right triangle ABC, and because of the fact that the area of the big right triangle ABC consists of also the area of this right triangle AQM, we have to subtract from the area of the big right triangle ABC the area of this white triangle AQM, and because of the fact that the area of triangle ABC doesn't include the area of this green right triangle PCM, we have to add to the area of triangle ABC the area of this small green right triangle PCM. So in total, we actually found out that the area of the green shape equals to the area of the big right triangle ABC minus the area of the small white triangle AQM plus the area of the white right green small triangle PCM. The area of triangle ABC equals to the base that is AB times the height that is CB over 2. The area of the white triangle AQM equals to the base that is AQ times the height that is QM over 2, plus the area of the green small triangle PCM, it is equal to the base that is PC times the height that is PM over 2. AB 6, CB 7, so in total the area of the right triangle ABC equals to 6 times 7 over 2. Plus the area of the right triangle QM, AQ is 5, QM is 10 ninths over 2. Plus the area of the green small triangle PCM, PC is 4 times PM is 8 ninths over 2. So in total the area of the green shape equals to 6 times 7 over 2 is 21. Here 5 times 10 over 2 times 9 is minus 25 over 9. And here 4 times 10, 8 over 2 times 9 is plus 16 over 9. So the area of the green shape in total equals to 21. Here 9 is a common factor from those two expressions. 9 is a common factor. So in total the value of those two expressions is equals to minus 25 plus 16, that is minus 9 over 9. Minus 9 over 9 is minus 1. So in total the area of the green shape equals to 21 minus 1, that is 20. So in conclusion, we found out that the area of this green shape equals to 20 square units. Okay, thank you very much.